This is Ramakrishna, Maths faculty. In this class, I am going to discuss about inverse functions. Let us start. Here I have written the definition of the inverse function. If f is mapping from a to b, be a function defined by y is equals to f of x, such that f is both 1, 1 and onto, that is bisective. Then there exists a unique function g is mapping from b to a, such that for each y belongs to b, there exists g of y is equals to x if and only if y is equals to f of x. For example, here f is the mapping from a to b. Here I am taking 1, 2, 3, 4 and here a, b, c, d. The image of 1 I am taking a, the image of 2 under fb, the image of 3 under fc, the image of 4 under fc or d. Now, this is 1, 1 and onto. Then there exists one function f inverse mapping from b to a. There exists only one function from b to a. And here, for each y belongs to b, g of y is equals to x. Here, f inverse of a is equals to 1, f inverse of b equals to 2, f inverse of c equals to 3, f inverse of d is equals to 4. So, this one we say inverse function, f inverse mapping. Here, f is mapping from a to b, f inverse is mapping from b to a. Here, which of the following functions have inverse? Now, we can discuss some examples here. First one, here mapping also very important. F is mapping from z to z, here integers to integers, defined by f of x equals to x plus 2. Now, the given function, is it satisfying bisective or not? First we have to check that one. Which of the following functions have inverse? If it is bisective, then only we can say the given function is invertible. Inverse exists for the given function only. Now, how to check that one? Like, you can take any two elements from the domain x1 comma x2 belongs to z, and for 1 1, for the checking of 1 1, here this one we say analytical method. F of x1 is equals to f of x2. F of x1, replace x by x1. x1 plus 2, that is equals to x2 plus 2. Here by removing 2, by cancelling that one, x1 is equals to x2. So here f of x1 is equals to f of x2. That implies if you get x1 equals to x2, f is said to be 1 1. Now for onto, here I am taking a letter y be an arbitrary element in the codomain. Here set of integers are there, here also set of integers are there. In the total function, x be an element in the domain, y be the element in the codomain. Here let the given function be y is equals to x plus 2, and here you can make x as subject, x equals to y minus 2. Here x equals to, we got y minus 2. Now, what is the pre-image of y? That is x. X equals to y minus 2 only. The pre-image of y is y minus 2. Now, for every y belongs to z, y minus 2, whether we are getting the integer, here domain integers are there. So, for every y belongs to z, whether we are getting the integers or not, we can check that one. For example, if I take 3, what is the pre-image of 3? 3 minus 2, 1. 1 belongs to z. Like that, you can take any integer, y minus 2 also belongs to integer. What is the meaning of that one? So here we can come to know that one, all the elements in the codomain, for every element in the codomain, there existing pre-image. For every element in the codomain, if there exists a pre-image, that one we say onto function. Here only we can come to know that one. Here y you can write the pre-image of y, that is y minus 2. So here you can take a different integers and see that one pre-image y minus 2. If it belongs or doesn't belong to integers. If it belongs to integers means for every element in the codomain there exists one pre-image only. So that is said to be onto. But while proving that one, here we have to write the steps. For every y belongs to z, there exists an element x is equal to y minus 2 belongs to z such that, after knowing that one, then only we can write the steps. Here what is the definition of the onto? For every y belongs to b, there exists an element x belongs to a such that f of x equals to y. For every y belongs to z, there exists an element x belongs to z such that f of x equals to. Now what about f of x given function x plus 2? Now here in the place of x you can put y minus 2. Plus 2 is there. Here plus 2 minus 2 both gets cancelled. F of x equals to, we are getting y. Therefore f is said to be onto function. So here f satisfying both 1 1 and onto, therefore f is said to be bisective. If it is bisective, inverse exists. Next one, f is mapping from z to z, f of x equals to 2x. Here in the domain integers are there, codomain also integers are there. By taking a different integers you will get a different images also. So how to prove that one? Let x1 comma x2 belongs to domain that is z, and f of x1 is equal to f of x2. That implies 2x1 that is equal to 2x2. Here 2 we can cancel. x1 is equal to x2. F of x1 is equal to f of x2. That implies if we get x1 is equal to x2, the given function is 1 1 function. Next onto. See, while writing this one, along with this relation, if we get one more relation, and if there exist some solutions in the given domain, that is not 1 1. Sometimes along with this we will get one more relation also, but there we won't get solutions in the given domain. That is 1 1. Next, for onto, we can discuss in the next problem also. That one. For onto, let the given function be y is equal to 2x. Here you can make x as subject to y by 2. Now here you can see the diagram. Here a set of integers are there in the domain. In the codomain also set of integers are there. X be the element in the domain and y be the element in the codomain. Here x equals to what we got? X equals to y by 2. Now here you can check. For every y belongs to z, there exists a pre-image integer or not. We can check that one. For example, if I take y is equals to 1, what is the pre-image of y? Y by 2. If I take y is equals to 1, 1 belongs to z only. What is the pre-image of 1? 1 by 2. 1 by 2 doesn't belong to z. And by taking odd numbers, 1, 3, 5, so on, they don't have pre-images. That pre-images we are getting 2n plus 1 by 2 doesn't belong to z. So at least one element in the codomain doesn't have pre-image, that is not onto only. But here most of all the odd numbers, they don't have pre-images. So this is not onto. Here we can write all the odd numbers in codomain doesn't have pre-images. Therefore, f is not onto. See, when we say the given function invertible, if it is bisective, here it satisfies only 1 1, not satisfying onto. So here this is not bisective, so inverse doesn't exist. Here f is mapping from z to z. F of x equals to modulus of x is given. Here also you can take, let x1 comma x2 belongs to domain that is z, and f of x1 that is equals to f of x2. What about f of x1? That is modulus of x1 that is equals to modulus of x2. Now, if I remove that modulus, x1 is equal to plus or minus x2. What is the meaning of that one? x1 is equal to x2 or x1 is equal to minus x2. Now here you can see, along with this we are getting one more relation also. Here x1 is equal to minus x2. If I take x2 is equal to 2, x1 equals to minus 2, both are there in the set of integers. By taking x2 is equal to 2, x1 is equal to minus 2, both are there. And x2 is equal to, if I take 5, x1 equals to minus 5, like that. Positive negatives are there, both are there. So we are getting the solution here and there also. If we get both the relations, if we get only one, x1 is equal to x2, then only we say the given function is 1, 1. Along with this, if we get one more relation, and here also if we get infinite solutions, then the given function is not 1, 1. Here we can show the one example also here. This is the general proof. By doing the general proof also we got that one. And f of 1 is equal to modulus of 1, that is equal to 1. F of minus 1, that is equal to modulus of minus 1, that is equal to 1. Here 1 is not equal to minus 1, but f of 1 is equal to f of minus 1. Different elements having the same image. What is the definition of 1, 1? Different elements having the different images. Here different elements having the same image, therefore it is not 1, 1. If it is not 1, 1, this is not bisective. And onto also here we can see, for onto also, maybe this one not satisfying, both 1, 1 and onto. Here set of integers are there, here also set of integers are there. Here positive integers are there, 0, negative integers also there. Here also positive integers are there, 0, negative integers also there. Here y is equal to modulus of x. Output you can get only non-negative real values. All the positive real values are associated to positive, 0 is associated to 0, all the negative real values are associated to positive real values. So here all the negative real values in the codomain, they don't have free images. Here what to write? Here range of the modulus function is non-negative set of all the non-negative real values. So the negative real values in the codomain, they don't have free images. So this is not onto, not satisfying 1, 1 and not satisfying onto also. Therefore inversion doesn't exist. The next problem. Here R minus element 3, B is equals to R minus element 1, and let f is mapping from A to B be defined by f of x equals to x minus 2 by x minus 3. Prove that f is invertible and find f inverse. How can we say the given function f is invertible if it satisfies both 1, 1 and onto? How can we say that one? How can we prove? How can we show the given function satisfying 1, 1 or onto? Just now we discussed that one. Again here also we can discuss. For a 1, 1, let you can take any two elements in the given domain. Here domain I am taking A only. x1 comma x2 belongs to A, where A is equal to set of all the real values except 3. And f of x1 is equal to f of x2. Here what is the function? X minus 2 by x minus 3. F of x1, how to get that one? Replace x by x1 only. x1 minus 2 by x1 minus 3, that is equal to f of x2. x2 minus 2 by x2 minus 3. You can take the cross multiplication here. x1 minus 2 into x2 minus 3, that is equal to x1 minus 3 into x2 minus 2. Here you can simplify this one. x1 into x2 minus 3x1 minus 2x2 plus 6, that is equal to x1 into x2 minus 2x1 minus 3x2 plus 6. Now simplify this one. Here plus x1, x2, x1, x2 both gets cancelled, 6 also gets cancelled, minus 3x1 plus 2x1. Both the x1 terms I have written one side and both the x2 terms you can write another side. Minus 3x2 minus 2x2 transpose that side. And here minus x1 that is equals to minus x2. Both the sides we can cancel the x1 minus x1 is equals to x2. Here we got only one relation. Here f of x1 is equals to f of x2. That implies here we got x1 equals to x2. Therefore the given function is 1, 1. Now we can prove, we can show that, and we have to verify that one, the given function satisfying onto or not. This is for 1, 1. For onto, the same procedure. Y be an arbitrary element in the codomain. Y be an arbitrary element in the codomain. For y belongs to B, there exists an element. Let y be an arbitrary element in the codomain such that here y is equal to, here for onto let the given function be y. Y is equal to x minus 2 by x minus 3, and here we can make x as subject to y into x minus 3, that is equal to x minus 2, x into y minus 3y, that is equal to x minus 2, and xy minus x, that is equal to 3y minus 2, x into y minus 1, that is equal to 3y minus 2, x equals to 3y minus 2 by y minus 1. Here x equals to what we got, x equals to 3y minus 2 by y minus 1. Here in the domain, set of all the real values are there except 3, here set of all the real values except 1. Now you can take, what is the premise of y? 3y minus 2 by y minus 1. By taking every real value except 1 and check that one here, 3y minus 2 by y minus 1, is it existing or not? But this one actually doesn't exist for 1, but 1 is not there in the codomain. Remaining here 3y minus 2 by y minus 1 exists for every real value except 1. So here all the elements in the codomain having the premise is 1. Therefore, for every y belongs to all the real values except 1, there exists x equals to 3y minus 2 by y minus 1 belongs to set of all the real values. Wherever we are taking y belongs to codomain, x belongs to domain. For every y belongs to B, there exists an element x belongs to. Here we have to prove that f of x equals to y. F of x equals to, what they given f of x? X minus 2 by x minus 3. Here we got x value 3y minus 2 by y minus 1, 3y minus 2 by y minus 1 minus 2 by 3y minus 2 by y minus 1 minus 3. And simplify this one, you will get we can get y only. For every y belongs to B, there exists an element x belongs to A, such that f of x equals to y. Therefore, the given function is onto. And here f is satisfying both 1, 1 and onto. So f is bisective. If it is bisective, inverse exists only. Now we have to find f inverse also. How to find? After completion of this one, you can write two statements. F is both f satisfying both 1, 1 and onto. F is bisective. Therefore, f inverse exists. Here we made x as subject. X is equal to 3y minus 2 by y minus 1. Now here you can see x is an element in the domain, y be an element in the codomain. F is mapping from A to B. Here y we say the image of x under F only. F of x equals to y we can say. And what about x? X is the pre-image or inverse image of y under F. That one we can write F inverse of y. Here y is the image of x under F. F of x equals to y we can write. And x is the pre-image or inverse image of y under F. That one we can write F inverse of y is equals to x. So in the place of x we can write F inverse of y, that is equals to 3y minus 2 by y minus 1. So to express in terms of x, replace y by x only. 3x minus 2 by x minus 1. This is the inverse function. The next problem, f is mapping from R to 1 to infinite, f of x equals x square minus 4x plus 5. Then find the largest possible intervals for which f inverse x is defined and find f inverse. Now here you can see, this one I am writing in the completing, here I am using completing square method. F of x equals to, here y is equals to f of x only, in the place of y, f of x you can write it y is equals to, this is x minus 2 whole square minus 4 plus 5. That implies y is equals to x minus 2 whole square plus 1. And x minus 2 whole square, that is equals to y minus 1. Here this one represents a parabola. This one represents parabola. And here what is the vertex of the parabola? X equals to 2, y is equals to 1. 2 comma 1, that is the vertex of the parabola. Here 2 comma 1, this is the vertex of the parabola. And the parabola symmetric about positive direction of y-axis. Positive direction of y-axis. Here 2 comma 1, this is the vertex of the parabola. Now here you can see, this is the x-axis. But here by considering total curve, that one not satisfying 1 1. Why? Because if I draw the line parallel to x-axis, that one cuts the curve more than once. So this is not 1 1. Here what they are asking, find out the interval. In that interval, the function should be bisective also. Now this is symmetric about positive direction of y-axis. You can divide into two parts. You can consider either that side or this side. If I consider this side, f is mapping from here minus infinite to 2, we are taking minus infinite to 2 tends to f is mapping from, this is the domain I am taking. Whatever the range, least value, corresponding y values, 1 to infinite we are getting, 1 to infinite. Or we can consider either that one or one more, 2 to infinite. F is mapping from here x values, if I take a 2 to infinite, tends to, then whatever the corresponding y values, here also 1 to infinite. 1 to infinite. Now here you can see, this is a symmetric about positive direction of y-axis. By considering total curve, that one not satisfying 1 1. Why? Because if I draw the line parallel to x-axis, cut the curve more than once. That's why this one I divided into two parts. Minus infinite to 2, 2 to infinite. Minus infinite to 2, whatever the corresponding value is 1 to infinite only. Either 2 to infinite also 1 to infinite only. Corresponding y values is same only. In this, here if I make x as subject here, if I make x as subject, x minus 2 whole square, that is equal to plus or minus here. If I take the square root, x minus 2, that is equal to plus or minus root of y minus 1. Here x is equal to plus or minus root of y minus 1 plus 2. Here plus 2, that is common only, everywhere plus 2, that is common only. But here plus or minus are there. Where we can get here x value, corresponding x value positive, if I take this one 2 to infinite, here x values, all the x values should be positive only. So here we can write x is equal to 2 plus root of y minus 1, both are positives only, we can get the positive value, x value, whatever you can take y values, corresponding x values are positive only. So here x, whatever x here, that is nothing but f inverse of y only. This is the one of the inverse function in this intervals. For example, here if I take here whatever x value, positive value I am writing 2, here I am taking minus root of y minus 1. Here corresponding, here x values, whatever you take y values in the interval 1 to infinite, corresponding x values you can get a negative, minus infinite to 2 only. So depends upon the interval, here we can write the inverse of the function. In this interval, this is bisective and inverse of the function. X is nothing but f inverse of y. In this interval, f is bisective and f inverse of y is equal to 2 minus root of y minus 1. And in this interval, the given function f is bisective and inverse of y, inverse of f inverse of y is equal to 2 plus root of y minus 1. How to know that one? Either plus or minus. How to know that one? Here all the corresponding, whatever we are taking 1 to infinity in the place of y, all the corresponding x values should be positive. That's why here plus I have taken, here minus. Next, here one more question. F is mapping from R to R be defined by f of x equals to e power x minus e power minus x. Here, so that the given function is invertible and find f inverse also. Now here you can see for 1 1 you can take any two elements in the domain x1 comma x2 belongs to R, and f of x1 is equal to f of x2. That implies f of x1 is equal to f of x2. That implies here e power x1 minus e power minus x1, that is equal to e power x2 minus e power minus x2. This one we can write e power x1, a power minus x we can write 1 by e power x1. That is equal to e power x2 minus 1 by e power x2. Now e power x1 minus e power x2, that is equal to, this one you can transpose that side, 1 by e power x1 minus 1 by e power x2. E power x1 minus e power x2, that is equal to, if I take LCM here, e power x2 minus e power x1 by e power x1 into e power x2. Next you can transpose that one this side, e power x1 minus e power x2 minus of, otherwise plus, transpose this side, I am taking plus common, e power x1 minus e power x2 by e power x1 into e power x2, that is equal to 0. So here from these two terms I am taking e power x1 minus e power x2 as common. E power x1 minus e power x2, if I take common, here we can get 1 plus 1 by e power x1 into e power x2, that is equal to 0. Here two solutions are there. Either this one equals to 0, e power x1 minus e power x2 equals to 0, or e power x1 is equal to e power x2, that implies x1 is equal to x2. Here x1 equals to x2 we got. And along with that, one more relation also there. We can check that one. They are existing the real solutions or not. 1 plus 1 by e power x1 into e power x2. That is equal to 0. E power x1, if I take the LCM, plus 1 is equal to 0, or that one is equal to minus 1 we are getting. Now here you can see, here I have taken the LCM, and that LCM I transpose that side, 0 and anything 0 only. Now here you can see exponential function, for every x belongs to R, exponential function always positive only. Here e power x1 that is positive, and e power x2 that is also positive. But positive into positive you never get negative value. Here the product minus 1 we got. So here we are not getting the solutions. So here we got only one real solution, that is x1 is equal to x2. F of x1 equals to f of x2, that implies x1 equals to x2. Therefore the given function is 1 1 function. Now we can see the onto function also. We can check the onto also. So here we can take, let the given function be y is equals to e power x minus e power minus ex. And here we can make x as subject only. Y is equals to e power x minus 1 by e power x we can take. Y is equals to e power x whole square minus 1 by e power x. So here what we are getting, e power x whole square minus y into e power x minus 1 equals to 0. Here we are getting the quadratic equation in terms of y, e power x. So by using the formula minus b plus or minus root of b square minus 4ac, here a is equals 1, b is equals minus y, c equals to minus 1, minus b, minus of minus y, plus or minus root of b square minus 4ac upon 2a. Here minus into minus plus. Why? But here plus or minus is there. Which one you have to select? Only plus. Why? Because exponential function never be negative. That's why in the plus or minus you can keep only plus. Here the plus root of y square plus 4 by 2. Now here I am taking log on both sides to the base e. Log x, log of e power x to the base e I am taking. Both the sides I am applying the log only. Log of y plus root of y square plus 4 by 2 to the base e. Now that is x is equal to log of y plus root of y square plus 4 by 2. Here what about x here? X is the f inverse of y only. X is the f inverse of y. Now the given function is, now here for on to here only we can check that one as x approaching to infinite by taking the larger values, e power x minus e power minus x also taking the larger values, by taking the negative values that one also as x approaching to infinite f of x tends to infinite, as x approaching to infinite minus infinite f of x also approaches to minus infinite. So the given function is on to f inverse exists only. And what about f inverse of y? X equals, we can write f inverse of y, that is equals to log of y plus root of y square plus 4 upon 2 to the base e. If you want the function f inverse in terms of x, replace y by x only. Next one, find the inverse of f of x equals to x if x is less than 1, x square, if x lies in between 1 to 4, and 8 root x is more than 4. See, here we have to find only inverse of the function. Here no need to check, verify 1 1 and on to 1. Maybe that is satisfies. Here they are asking for directly find the inverse of the function. Now for inverse we are taking, let the given function be y is equal to f of x, and here x we say that is the inverse of y only. By making x as subject, that one we say f inverse of y. Now f inverse of y that is equal to, here let the given function be y is equal to f of x, y is equal to x, and here x is the f inverse of y, f inverse of y is equal to y. Here x equals to, I got y, y less than 1, and next y is equal to f of x, y is equal to, what about f of x here? X square. By making x as subject, x equals to root y. What about the x value? That is f inverse of y. F inverse of y, that is equal to root y. The inverse of the second function, that is root y. 1 is less than or equal to, what about x value here? X equals to root y, less than or equals to 4. And y is equal to f of x, y is equal to, what about f of x here? 8 root x. And if I make x as subject, y square by 64. So x is the inverse of y only, y square by 64. And what about x value? X equals to y square by 64 is more than 4. Now here you can simplify this one. Y is less than 1. For all the real values less than 1, the inverse of y, the inverse of f is equal to y, and root y, here squaring, both the sides pursues are there. So 1 is less than or equal to, y is less than or equal to 16. Next here, y square by 64, y square is more than 256, y is more than 16. This is the inverse of y. Sorry, inverse of f. Here find the inverse of f is mapping from -1 to 1 tends to -1 to 1. closed brackets both are. Here f of x equals to x square into signum of x is given. F of x equals to x square into signum of x. Here we can redefine this function. F of x is equals to, here we know the signum of x. If x more than 0, signum of x equals to 1 into 1 if x is more than 0. And if x equals to 0, signum of x equals to 0 only. So 0 and anything 0 we can get. And signum of x equals to minus 1 if x is less than 0. If x is less than 0, signum of x equals to minus 1 minus x square we are getting. Now here I am combining these two. That is equals to, here we can write x square, x more than 0. And if x equals 0 also we are getting the 0 only. More than 0 to up to 1. So here x belongs to 0 to 1. That is x square. Here I combine these two. And for x less than 0, minus x square only. So x belongs to minus 1 to 0. This is minus x square. Here we can include 0 in both the cases also. Now this is f of x. And what we have done previous, see, we can write x belongs to 0 to 1 or 0 is less than or equals to x is less than or equals to 1. Here minus 1 is less than or equals to x is less than 0. We can write in like that. Now y is equals to f of x and inverse of f, x equals to f inverse of y only. Generally we are taking y is equals to f of x. So here y is equals to, whatever the function, x square. Whatever x is equals to root y. That implies that is equals to, what is the inverse of this one? F inverse of y, that is equals to root y. Now 0 is less than or equals to, whatever x value, root y. Less than or equals to 1. And here by taking y is equals to f of x, y is equals to, what about f of x here? Minus x square. Now x square is equals to minus y, x equals to root of minus y. X is the f inverse of y only. F inverse of y, that is equals to square root of minus y. Square root of minus y. And here you can see one thing. X less than 0 only. Corresponding x value. Here corresponding x value should be negative. Here actually we will get a plus or minus here by taking x equals to plus or minus. But x should be negative. So here you can consider negative. Out of the two you can consider negative. Minus root of minus y, where minus 1 is less than or equals to, what about x value? Minus root of minus y is less than 0. So this is f of x. Now f of x equal, this is f inverse of x. F inverse of, this is f inverse of y. Now here I am writing f inverse of y, that is equals to root y. By squaring on both sides, all are positive only. By squaring on both sides, 0 is less than or equals to, y is less than or equals to 1. By simplifying this one, by simplifying that one, here we can get, here minus root of minus y, here we can get minus 1 less than or equals to y less than or equals to 0. Here actually 0 included in both the intervals also. So this is the, here you can simplify both. Then we can get this one. So in this class we learned inverse trigonometry, how to find the inverse of a function if different functions are given. In the next video class I am going to teach periodic functions.